Hello everyone, my name is Long, and our team consists of myself, Timothy, and Amado. We're presenting to you our course project to optimize the length and thickness of a spoon to prevent the spoon from bending while scooping ice cream. So to introduce you to the problem, ice cream scoops are designed to put all the force at the weak wrist joint of the spoon, as you can see in the image. And when this happens, it makes the scooping action difficult, and it hinders the consumer ability to leisurely enjoy their ice cream without worrying about a catapulted action or the spoon bending or snapping. And what the customer need is a spoon that can structurally withstand the prying force of an average spoonful of ice cream. And how the spoon functions is when a spoon is used to scoop ice cream, it's usually come from an angled position, and the largest prying force is exerted when the spoon is inserted at a 90 angle degree.
All right, so here we're going to start talking about our assumptions and boundary conditions. Starting off our geometry, we got this spoon model from just a GrabCAD link there. It's pretty generic, has the handle and scooping part of the spoon, and we thought it represented just the general spoon you would find in your house or at a restaurant. And so we chose that, and then we just modified the various dimensions, as you will see. For our variables, the material we chose was stainless steel grade 430, and we chose this because usually we find spoons are made out of a slightly cheaper grade, and so we chose this instead of a more strong one, just to once again accurately represent the spoons that you might find in your house. For the load, we chose 150 pascals, which was applied uniformly on the main part of the handle. We didn't apply anything at the tippy top or the wrist of the spoon, just because, once again, we were thinking about where you put your hand on the spoon. And as you can see on the right there, it's the red section with the orange arrows. And we felt that that was the place where most people's hands are going to be. As well, we did some research into it, and 150 pascals is 2/3 of the maximum grip force of the average human. And so according to our research, that's what we found was reasonable for humans to scoop ice cream with, based on some studies we read. Finally, the boundary conditions is what you would expect. It's the scooping surface that will be stuck into the ice cream, and that is shown in the image on the right there in Abacus with the orange and blue arrows, and it's just encapsulated. So all the degrees of freedom are fixed there because, once again, that's what's going to be stuck in the ice cream in an ideal situation, and none of that's going to move. And so we just had a pressure distributed load as well there, and you can see the magnitude that we inputted.
And to the design variables that we are trying to play with here, you can see in the image is the spoon from GrabCAD earlier, and we are trying to optimize two variables. One of them is the handle length, which is from the bending portion of the spoon to the tip of the spoon of the handle, and second is the thickness of the spoon at the bent position, bent portion.
For this project, we're going to be trying to optimize the total volume that the spoon is. Our parameters are going to be changing both the length of the handle and the thickness of it. And then with the optimization statement in MATLAB, we are also going to be constraining by the bending stress of the spoon. For this portion, we had taken the yield stress as the maximum as we would want the spoon to not be able to bend from the force of the scooping. The yield stress was found online as 215 megapascals, and this is the yield stress for stainless steel. The length bounds were found for the average size of a human hand as being the lower bound, and then we decided to double that to be our upper bound. While using these parameters, we performed analysis on Abacus for 3 different tests, one as our control, one where we increased the thickness of the spoon, and one where we had increased the length of the spoon. With each change, the team had measured both the volume and bending stresses for each test. Using both the volume and stresses, we were then able to formulate the Fourier equations. For this, we would have derived both the volume and stress equations to find the units needed for the Fourier equation seen in the next slide. Here we perform the calculations, and this is what we used to develop our Fourier equation. And then for this, we had taken all the values from the previous slides and formulated the equations for the MATLAB portion of this project.
So you may ask, why are we doing this project? What's the benefits? And the answer for that is, when we design a spoon with optimized thickness and length, it enable us to have less chances of failure due to prime load. First, and it enables customer to scoop larger spoonful of ice cream, and that will lead to more enjoyment in dining. Second is enable consumer to save money on buying more spoon because of their spoon snapping or bending. Third, if we have higher quality spoon, which means less people buying more spoon, we have less volume of production, and that leads to less manufacturing waste, and that will result in a positive environmental impact. And fourth, smaller volume production also means that less spoon is being shipped, and that will reduce the logistic cost for the spoon company.
Next up is our Abacus analysis and our results from the simulations we ran. The first picture on the top right is going to be the standard spoon. The one in the middle is going to be the thicker spoon with the standard length, and then the one on the bottom is going to be the longer spoon with the standard thickness. And so as you can see there in our results, the magnitude is the largest at the end of the handle, which is matching our intuition. So it's always good when the simulation confirms that. As you can see there, it's pictured on the right. And then yes, the distribution was pretty similar among all the cases as the colors change from blue to green to yellow to red. Among all three of them, that was pretty similar. There were, slight differences among the different magnitudes, but overall the deflection increased on the further away the handle it was. Next up is going to be the stress analysis, and so the main conclusion was the thicker and shorter the spoon is, the less stress it experiences. And so once again, there you can see this pictured on the right. And if you have any questions about, if it's to scale or not, some of the angles of the screenshots were difficult to get, so they might not look all, exactly right, but it does match the numbers we showed on the earlier slides. And also, the distribution here, once again, was pretty similar among all the different cases. And this makes sense, because there's not that big of a difference between these geometries. The most stress was concentrated at the wrist joint of the spoon, which once again confirms what we were saying earlier, and confirms a real life experience of the wrist joint bending and being the first to bend.
Okay, so taking both the constraints and the Fourier equations we developed, we were then able to implement this inside of a MATLAB code. This was then used to find the optimized thickness and length of the spoon regarding our volume, our total volume. In our optimization results, we saw that a thickness of 1.36 millimeters and a length of 90.32 millimeters were the best combination for optimizing the total volume, and seeing that the spoon was still unable to bend.
Yep, in conclusion, it was interesting to find out that what we initially thought was to decrease the length of the spoon and increase the thickness, and this was true in regards to the MATLAB optimization. In order to optimize the volume, we saw an increase in the thickness slightly and a decrease in the length, and this was further proved from the Abacus experiment, where the thicker spoon saw a smaller stress number, while a longer spoon saw a higher stress number than the original spoon. And if you want to get a spoon that you can soundly eat ice cream with, go for a short and thick one. Thank you for listening.